Let's proceed to the last part of this chapter, which is about overloading function names. What is overloading? In C++, we can have functions that have more than one definition, which means we can name a function and have multiple versions of it. This is quite useful for situations in which the same function is needed for different numbers or types of arguments, which means this would allow us to write different versions of the same function that we can use for different scenarios. Overloading a function name means providing more than one declaration and definition using the same function name. Here's an example. For instance, we have the function named average. We have the following return type and of course the parameters that are required by the function and of course its function body. Here's another function with the same name and the same return type. However, if you'll notice, we now have three formal parameters as opposed with two in the previous version of this function. In this case, the compiler checks the number and types of arguments in the function call to decide which function to use. For instance, we have the following function call as a part of this cout statement. After seeing the number of arguments that are passed to this function, what our compiler will check if there is a version of this function with three arguments. In this case, it will use that version of the function with the same number of parameters, which is this one. That is one example of how overloading works. As you can see, we have the same function name, but overloading allows us to create different versions of it. Here are some details about overloading. Talking about overloaded functions, they must have different numbers of formal parameters and must have at least one different type of parameter. However, they must return a value of the same type, just like this one. As you can see here, we have the function average, and each version has different numbers of parameters, although we must take note that they must always have the same return type. Going back to our pizza buying program, we can actually improve that using the concept of overloading. In this case, we now have the following modifications. If we will recall, we have the following function, unit price. Let's take a look at this implementation. If you will take a look at this, we now have the new version of our function unit price, but this time we now have three formal parameters, which means every time our compiler sees a function call which contains three arguments, it will look for the appropriate version of that function and use that. For example, we have here a function call which involves three arguments. What our compiler will do is it will look for that version of our function which contains the same number of arguments, and whatever is contained in our function definition, it will be executed just like this one. Again, I would like to try and run this program by yourself, and of course explore the code and try to see how function overloading works. We also have what we call automatic type conversion. For instance, we have the definition for the function MPG. As you can see, what it does is calculates the miles per gallon consumption of a vehicle. It has the return type, the name, and of course, the parameters that are required, which in this case, we have two parameters. The question is, what will happen if MPG is called this way? In this case, we provided two arguments but of type integer, although in our definition here, the parameters were declared as double. Given this function call, the values of the arguments will be automatically converted to type double, since in the definition of our function, the parameters were of type double. Now, what will happen if we introduce another definition for this function? This time, we have the same number of arguments, only that they now have integer data type for our parameter list. And of course, it has the following definition, which is actually measure of perfect goals as opposed to miles per gallon from the previous example. Now, what will happen if MPG is called this way? As you can see here, we have the same function named MPG, but this time it is provided with arguments of type integer, although what we would like to output here is actually the miles per gallon. What will happen is that the compiler chooses the function that matches parameter type, so the measure of perfect goals is the version that will be used instead. So the lesson here is that we should not use the same function names for unrelated functions. As you can see here, miles per gallon is completely different from measure of perfect goals. And of course, they are completely unrelated from each other as far as logical use of such name is concerned. Therefore, we must avoid such scenario in order for us to avoid the type conversion problem in which the compiler will choose the version of the function that matches the parameter type that was provided in the function call. That ends the last section of this chapter. In this section, it is expected that we now understand the concept of top-down design. If we will recall, in the pizza buying program, we broke down a big problem into smaller subtasks, and of course, we were able to translate each subtask into a function of its own. Also, we now know how to describe the type of task that we have seen, which also satisfies the concept of top-down design, in which we broke down one huge problem into smaller, more manageable subtasks that later on translates into an actual solution to our programming problem. We were also able to understand the principles of black box, procedural abstraction, as well as information hiding. Also, we were able to see the difference between local variables, global constants, as well as global variables. And finally, we were able to understand function overloading, as well as how to properly use overloading and some things that we need to remember when we are dealing with overloaded functions.